I ended the last video with the effect of arrangement of sources to the electromotive force of the energy source in a circuit, and this was the summary of possible things that could happen when the dry cells of different values are connected parallel to each other. Charging of the weaker dry cell by the dry cell with the higher EMF would take place. It is kind of dangerous in the sense that the weaker dry cell would become very hot. In some cases, it could even explode. And lastly, as suggested by the hotness of the circuit components, the electrical energy of the dry cells are just wasted. Now, apart from the EMF, there is another term that you guys should be familiar with in this chapter about current electricity. It is with this load or component here. How could an electron, this one, the yellow dot, how could it go from this point to that point across the component? Here we need an energy to do work to bring the charge from this point to that point or across the component, which looks very similar to how we deal with and define the EMF by looking at the work done by the source to move a charge through the circuit here. All right, let's focus on these and do more definitions for these components. At this part where the source is, we have the electromotive force, which has already been defined as the work done by the source in moving charge throughout the entire circuit. Now, in the case of the circuit component here, the work done, as in this symbol, to drive charge through the component, say electrons from this part of the component to that other part of the component, is the potential difference, or otherwise known as the voltage across the component. Since these different quantities have similar terms, similar, okay, not the same, which are included in their definitions, and as can also be inferred from the formulas, we could say that they have the same units, joule per coulomb, and that 1 joule per coulomb is defined in the SI system as equal to 1 volt here. All right, let's move to the tools. These are what we commonly have in laboratories in schools. It is easy to know whether it is for current or potential difference, voltage, and EMF based on the unit shown at the display of the device. This one is V, so this must be a device that measures a quantity that has that unit. Should be EMF and potential difference, and this is called voltmeter. This other one has this A, which means ampere. It measures a quantity that has ampere at its unit. This device is called an ammeter, which is used to measure current. When you place them in circuits, these are the symbols used for them: ammeter here and voltmeter here. Apart from the symbol, note also how they must be connected to the circuit. A voltmeter must be connected like that, and ammeter is like that. One in series, the ammeter, the other parallel with the component of a circuit, the voltmeter. Okay, let's do a practice here. This is a simple circuit diagram with an energy source providing the EMF here, a switch with two bulbs connected parallel to each other, and a resistor here. It is a diagram that represents an actual one like this, also with the source, switch, two bulbs, and a resistor. And a new one here, an ammeter. Let's change the diagram a while ago. Let's place an ammeter here in series. So there we have an equivalent diagram to the actual one. Now let us place a voltmeter across the energy source like that and see how we should implement that in the actual circuit. Here, we take that voltmeter and place one terminal here and the other here, and we have the electromotive force of the source. Notice it reads the EMF even when the switch is off. When it is on, same value will be measured by the voltmeter. That's for the EMF at the source itself. How about across a component of circuit? Let's try using voltmeter across this component here. Let's move this terminal here, the other at the other end, and there we have a reading, 12 volts. This is happening because the circuit is closed. Let us see what will happen if the circuit is open. Switch off, and there we do not have any value. It only shows that this potential difference or voltage are only there when it is provided by the source. We had 18 volts EMF, and that here 12 volts of that is being used here when the circuit is on. The remaining 6 volts must be in use by other components. Let's check by taking the voltage of the other components. Here we move the terminals once again, but we do not have any reading. Yes, because the circuit is open, we must switch it on like that, and there we have 6 volts. And so we have another voltage here, let's call it V. And since this has different value as compared to the other V there at the resistor, we can use subscripts here like that. Alright, before ending this video, let's take a look at the potential difference across the combination of bulbs here, connected parallel with each other. As you can see here, they are parallel in the actual C. There we have 6 volts too. Okay, for the idea why this combination has 6 volts, we will reserve the discussion for our other session. And in that, you will also see that the other bulb will have 6 volts potential difference too. Meantime, just remember how voltmeter is used. That is always parallel with the component while ammeters are in series. As for opening and closing the circuits by manipulating the switches, for the voltmeter, it measures the EMF of the source whether it is on or off. And for individual components, to measure the potential difference or voltage across each, the switch must be on. Okay, that's all for this video, guys. Bye.